Well, welcome back. We're continuing our discussion of the semiconductor equations, and in this lecture I'm going to discuss a very powerful qualitative way to understand the solution to these equations. This is perhaps the most important lecture of this course. If you understand energy band diagrams, you can really go a very long ways towards understanding the operation of a semiconductor device. We have these equations. This is a fairly complicated set of mathematical equations, but we know if we solve these equations, we can understand the operation of any device. But we're looking for a way to avoid a lot of mathematics in this lecture, and we're looking for a way to get some qualitative insight into the solution to these equations. An energy band diagram, I'll just remind you, we have an energy versus momentum, or an EK plot, that describes the band structure of a semiconductor. But an energy band diagram is a plot of the bottom of the conduction band and the top of the valence band versus position. So these energy band diagrams we're going to see in this lecture are a very powerful qualitative way to solve these equations. And just to make that point, I'll quote Herbert Kroemer, as a very famous semiconductor physicist who actually won the Nobel Prize for his work in semiconductors. And he makes this point when he teaches semiconductors to his students. He says that if you're discussing a semiconductor problem, and if you can't draw the energy band diagram, it really means you don't know what you're talking about. Now, he also has a corollary. He says, if you can draw an energy band diagram, and you're talking to someone about a semiconductor device and you don't draw that energy band diagram, then the person you're talking with won't understand what's going on. So energy band diagrams really do form a central way that electrical engineers and device physicists have learned to understand semiconducting devices. Now, there'll be a very important principle when we draw these energy band diagrams in equilibrium. And that principle I can illustrate here. Here's an energy band diagram. This is a plot of conduction band versus position, valence band versus position. I've shown the intrinsic level versus position there also. So it may describe some semiconductor. Now, if I look at a particular energy here, E1, and maybe look at this position, X1, and look at this position, X2, the probability that the state at position X1 and energy E1 and the state at X2 and energy E2, the probability that they're occupied in equilibrium must be the same. Otherwise, electrons would tend to move from one or the other, from high concentration to low concentration and fill them up. So the fact that they must have the same probability of occupation, and the fact that in equilibrium their probability is given by the location of that energy with respect to the Fermi energy, means that the Fermi energy has to be constant in equilibrium, such that there's an identical probability that a state at any energy is occupied always the same way, no matter how the bands are bending between those two locations. Okay. Well, this is actually a really important principle. The Fermi level is constant in equilibrium. Out of equilibrium, technically, there is no Fermi level. There's an analogous quantity we call the quasi-Fermi level. There's actually two, one for electrons and one for holes. We've discussed this earlier. When we derived the current equation, we said we know that in equilibrium there can't be any current. And that led us to conclude that the slope of the quasi-Fermi level, which is the Fermi level in equilibrium, had to be zero. And we concluded from that argument that the Fermi level is constant in equilibrium. All right, so two different ways of arriving at this very important conclusion. The Fermi level is constant. That's going to help us draw these energy band diagrams. Now, this concept of band bending is very important. And what do I mean by band bending? So this is a semiconductor, just a uniform semiconductor, doped p-type. The Fermi level is down here below the intrinsic level, close to the valence band. Everything is independent of position. The bands are not bending in any way. Now, if I were to put, say, an insulating layer on the surface of this semiconductor and a metal plate, and if I were to ground the end of the semiconductor on the right side, so that I have a reference for the voltage. And if I were to apply a positive voltage to this metal plate, which I'll call the gate, this is actually the heart of a MOSFET, a metal oxide semiconductor field effect transistor. But you can see that if I apply a positive voltage to the gate, there will be a positive potential that will influence this side of the semiconductor, but eventually the potential will go back to zero deep in the semiconductor on the right side. So if we ask ourselves what happens, we need to know what voltages do to energies. And you'll remember from freshman physics that if you have a positive voltage, that would attract and pull an electron towards it into a potential well. It would lower the potential energy of the electron. Okay, so energy is equal to minus Q times voltage is the principle we're going to use. Well, it's easy to see what the voltage does. It's got to be positive on this side of the semiconductor, get less and less positive, and then go to zero where we have grounded the back of the semiconductor. So it's going to do something like this. It'll be more positive as we go towards the surface of the semiconductor. Well, energy is minus Q times voltage. If the energy is more positive near the surface, the energy is going to be lower near the surface. So if I have an electrostatic potential increasing with position as I go towards x equals 0, I'll have energy bands that bend down. So when I see an energy band diagram that looks like this, the bands are bending. So this is a more interesting energy band diagram. This is actually the energy band diagram of the heart of an MOS field effect transistor. And when I see bands bending like this, I know that there is a position-dependent electrostatic potential which is responsible for the bending of the bands. So that comes from this simple relation between the electron potential energy and the electrostatic potential. Okay. Now I also know that if I look at the slope of this, that if I take the slope of this conduction band, well, this is EC at infinity, that's my reference, that's independent of position. So when I take the slope, I'm only going to be differentiating the electrostatic potential. I'll get a minus Q times the slope of the electrostatic potential. Minus the slope of the electrostatic potential is the definition of the electric field. So the slope of the conduction band will be Q times the electric field. Now all the bands, the valence band is just one band gap below the conduction band, so the slope of the valence band would give me the electrostatic potential also. The slope of the intrinsic level would give me the electrostatic potential. So just by taking the slope of the energy band diagram, I can determine what the electric field is in the semiconductor. I can also determine the electron density, because I know that the electron density is related to the position of the Fermi level with respect to the intrinsic level. So if I look back here on the right, deep in the semiconductor, I can see that the Fermi level is below the intrinsic level, meaning it's far away from the conduction band. I have a small number of electrons, but the Fermi level is close to the valence band. I have a large number of holes. So this semiconductor is p-type. There's a large number of holes deep in the semiconductor. As I move towards the surface, you can see that the Fermi level with respect to the intrinsic level is getting closer and closer. At this point, the Fermi level is equal to the intrinsic level. At that point, the semiconductor is intrinsic, and I know that N is equal to P is equal to Ni. As I continue to go towards the surface and the bands bend down more and more, the Fermi level is way above the intrinsic level. That means I have a lot of electrons. It's getting closer and closer to the conduction band. So this semiconductor actually has a lot of electrons near the surface, a lot of holes in the bulk. We would say that the surface is inverted. We have inverted a p-type semiconductor and made it an n-type semiconductor near the surface. And we can read all of that off of this energy band diagram. So when we encounter a semiconductor problem, the first thing that we will try to do is to draw the energy band diagram. After we've drawn the energy band diagram, we will read the energy band diagram to extract the quantities of interest. We know that when the potential goes up, the electron energies go down. So if I want the electrostatic potential versus position, I'll just flip the conduction band upside down, or the valence band, or the intrinsic level. It doesn't matter. We know that the slope of the conduction band, or intrinsic level, or valence band is proportional to the electric field. So we'll just take its slope. We can sketch the electric field versus position. And we know that the electron density and the hole density are related to the separation between the intrinsic level and the Fermi level. So, and there's an exponential relation there. So the log of the electron concentration is just proportional to the difference between the Fermi level and the intrinsic level. Same thing for holes. Finally, if I'm interested in the space charge density, well, the space charge density is the slope of the electric field. The electric field is the slope of the energy band. So the space charge density is proportional to the second derivative. Now, that actually can be a little bit difficult if we're sketching an energy band diagram. To take its second derivative can be, a little difficult to do accurately. Sometimes there are other ways that we can sneak up on the space charge density. All right, so for practice, take this energy band diagram and just run through. Make a plot of the electrostatic potential versus position, electric field, electron density, hole density, and space charge density. So I'll let you think about that. That's good practice. Let's talk about another example, and we'll run through that example in a little more detail, and you can see how this all plays out. So this is actually a semiconductor device. It's a junction between an N-type semiconductor that's uniformly doped and a P-type semiconductor that's uniformly doped. And this is actually a semiconducting diode that does useful things like rectify current, or if we shine light on it, it becomes a solar cell. But, the topic that we'd like to discuss is, what does the equilibrium energy band diagram look like for this semiconductor device? Just an example of what one device might look like. Well, we know far from the bands, far from the junction, the region over here, the semiconductor isn't going to realize that there's a junction over here on the right. So this will just look like a uniformly doped N-type semiconductor over on the left. Far to the right, it'll just look like a uniformly doped P-type semiconductor. In the middle, the bands will bend and something different will happen. Then the energy band diagram will become more interesting. How would we draw the energy band diagram for this device? Well, the first thing we do is we remember in equilibrium, the Fermi energy is constant, so I'd simply draw a straight line. That's my equilibrium Fermi energy. Okay. The next step would be to draw the bands where we know them. So we know that the semiconductor is N-type, far from that junction over here on the left. So I would just draw a conduction band near the Fermi energy and a valence band, a band gap below that. Over here on the right, I know the semiconductor is P-type, so I would draw a valence band near the Fermi level, and I would draw a conduction band, one band gap above that. And then we would smoothly connect those two in the transition region. Then we'd have our energy band diagram, and then we would read it to determine the various quantities of interest. Instead of solving those semiconductor equations, we would extract them from the energy band diagram that we had sketched. Well, this is the process. If you go through that process, this is the energy band diagram that you will come up with. Out here on the left, we're an N-type semiconductor. The Fermi level is near the conduction band. Out here on the right, we're a P-type semiconductor. The Fermi level is closer to the valence band. In between, we just make sure that everything smoothly connects. The bands will have to bend in order to smoothly connect the bands on both sides of this junction. This is our energy band diagram for a p-n junction, and we can read this energy band diagram and effectively solve the semiconductor equations. So, of course, the answer is easy out here in the N-type region where things are flat, and they're easy out here in the P-type region where the bands are flat. They get interesting in this transition region where things change. So let's read this energy band diagram and determine the electrostatic potential versus position, the electric field versus position, the electron and hole densities versus position, and the space charge density versus position. We could get all of these mathematically by solving those complicated semiconductor equations, but we can get them qualitatively simply by reading the energy band diagram. All right, electrostatic potential. So we remember that when the potential goes up, the bands go down. So if I want the electrostatic potential versus position, all I have to do is to flip the conduction band or valence band or intrinsic level upside down. All right. So if I do that, This is the electrostatic potential versus position. Remember, voltages are always relevant to some reference. It's only a difference in voltage that matters. So there's some arbitrary reference. I might make it 0 here. That might be more convenient. But we know that as the conduction band bends down, the electrostatic potential goes up. So this is what the electrostatic potential would look like versus position in this p-n junction. It's kind of interesting. You can see that there is actually a voltage difference across this p-n junction. That's called the built-in voltage of this p-n junction. Okay. How about electric field? Well, we remember that the electric field is proportional to the slope of the conduction band or the valence band or the intrinsic level. So there will be no electric field in the bulk N region. There will be no electric field in the bulk P region, but there will be a positive electric field in the transition region because the slope is positive there. So if we sketch that electric field versus position, we will see there's a peak near the junction. There is some transition region right around the junction. The electric field gets stronger and stronger and then drops and gets weaker and weaker. So that's qualitatively what the electric field versus position would look like. Finally, let's ask what the carrier densities look like. Carrier densities are related to the position of the Fermi level with respect to the intrinsic level. Out here I have a lot of electrons. As I move towards the junction, the Fermi level is not as high above the intrinsic level as it used to be over here on the left, or alternatively, it's much further away from the conduction band than it is here on the left, so the electron density drops. When I get here in the p-type region, the Fermi level is way below the intrinsic level, even further below the conduction band, so the electron density is very small. So the electron density will go from high to very small. The hole density will do the opposite. It'll go from high on the right and become very small on the left. So if we just sketch those out, we have qualitatively the electron concentration versus position and the hole concentration versus position in the p-n junction. Okay. Now, the next step, the final question I asked is, what does the space charge density look like versus position? I could try to take the slope of the electric field that we've drawn and use Gauss's law, divergence D is equal to rho, or the second derivative of that conduction band profile that we sketched. But taking that second derivative is kind of difficult and it might not be very accurate. Another way to do that is to recognize that this is a log plot. So on this region, I can see that in this transition region, I'm going to have exponentially fewer electrons on this side. But this is an n-doped region, so I still have those positively charged donors there. So I expect a positive charge on this side. On this side, deep in the semiconductor, I have lots of holes, I have lots of negatively charged acceptors, but as I get in this transition region, I have exponentially fewer holes. I still have those negatively charged acceptors, so I would expect a negative space charge on this side. Okay. So my space charge density, then I can use those arguments, and instead of taking the second derivative of this energy band diagram, I could do it through the carrier densities, and if I do it that way, there'll be a region here where the charge is almost entirely due to the ionized dopants, the donors that have positively charged on the N side of the junction, and on the P side of the junction, the charge will be due almost entirely to the ionized acceptors, negatively charged. So my space charge density would look something like that. And in the bulk of the semiconductor, we would be space charge neutral, just as we've always assumed for a uniform semiconductor. Okay, so how would we actually compute these quantities instead of sketching them? Well, we would solve these complicated equations. But before solving those, it's useful to sketch an energy band diagram and to understand qualitatively the nature of the solutions that are going to come out. Now, another problem that you might practice on, and we can actually get a little bit of insight into semiconductor physics from, is this problem. Let's say I have a semiconducting device and I have doped it very heavily near the surface and then less heavily as I move into the semiconductor. So I have a position-dependent doping density. Those acceptors give me a position-dependent hole concentration. and let's draw the energy band diagram for that. Well, I won't do that, but I'll ask you, draw the energy band diagram in this situation. You'll have to draw it in a way that you're uniformly p-doped here, and you're much more heavily p-doped here. If you draw that energy band diagram, and then you read it, you will see that there is an electric field present here. Right? Now you might ask yourself, where does this electric field come from? Well, we can understand that qualitatively. We have doped the semiconductor non-uniformly this way. The doping produced mobile holes. Those mobile holes are free to diffuse. They're going to diffuse from high concentration to low concentration. So they're going to begin to move into the semiconductor. So we're going to have fewer holes here because they've diffused away. We're going to have more holes here because holes have diffused down the concentration gradient. Well, this is going to set up a charge imbalance. We have more negatively charged acceptors here than we do positively charged holes. So we're going to have a net negative charge in this region. Over in this region, we have more positively charged holes than we have negatively charged acceptors. So we're going to have a net positive charge. A positive charge and a negative charge are going to set up an electric field. The electric field is going to put a force on the holes that will push them back to the left and stop them from diffusing. This is the origin of the electric field. It's going to, there will be a short transient, diffusion will occur, charge will be uncovered, an electric field will be produced. The electric field then will act to stop that diffusion process and hold everything in place. When we're all done, the the hole concentration will be approximately equal to the doping density, but not exactly. We'll say that the semiconductor is quasi-neutral. It is also almost neutral, but there is a small charge imbalance that produces an electric field that keeps everything in place so that the mobile holes don't continue to diffuse. Okay, so this is the result of, in equilibrium, we have to have zero net current. So this is the electric field that will give us a drift current to the left. There will be a diffusion current to the right, and the two will balance and we'll get zero current in equilibrium. All right, just to summarize this concept of drawing energy band diagrams and understanding qualitatively the solution to these semiconductor devices is an important skill. It is the way that semiconductor people understand and think about semiconducting devices. Okay, so the next topic, we have mentioned from time to time this idea of generalizing the Fermi level to quasi-Fermi level when we move from equilibrium out of equilibrium. I'd like to say a few more words about quasi-Fermi levels and their usefulness in semiconductors, their interpretation out of equilibrium. That'll be the subject of the next lecture. I'll see you there.